First up, I would like to introduce Jonathan Cannon. He is a postdoctoral associate studying prediction of autism spectrum disorders in the Sinha lab at MIT. He's also working with Anirudh Patel on neural models of beat-based timing. Outside of his academic pursuits, he plays rhythm on violin with Boston klezmer band Ezekiel's Wheels. He'll be discussing a Bayesian filtering framework for neural and sensorimotor entrainment. Jonathan, please go ahead. Is there a problem with the screen share, Jonathan? We can't hear you.
Unmute. Okay, sorry about that. There's my screen share. There we go. Okay. Sorry about the delay there. All right. Hi, thank you so much for coming. This has been some modeling and computational work that I've been doing over the pandemic, and I'm really excited to get any feedback on it that you're willing to share. So as my jumping off point, I'm asking the question, what is optimized by entrainment, both neural and sensory motor? And here I'm defining entrainment as the temporal alignment of a biological or behavioral process with irregularities in an exogenously occurring stimulus. It's a pretty general definition. A common example is tapping along with a metronome. And in that, a common way of understanding that behavior is that I'm minimizing timing error between my taps and the clicks of a metronome. But thinking about it this way generalizes poorly, because you can entrain continuous movements to periodic sounds. You can tap on the offbeats of a metronome and not try to align the sound in your taps. All of those are entrainment type behaviors. And so a way that I found really useful to think about this is as having an intermediary step where we're continuously estimating the phase of an underlying cycle. And then that estimate is now informing our behavior, which we can optimize in different ways based on that estimate. This allows us flexibility of our behavioral goals in entrainment. So formalizing it like that, we actually end up with a pretty nice mathematical statement of what it is we might be doing in entrainment. So if we suppose that a stimulus is based on some hidden phase, phi, that advances sort of like a clock, or along the real line, but advances steadily underlying the stimulus, then we can continuously infer a distribution on that phase based on noisy sensory measurements using Bayesian methods. And that inference effectively amounts to that intermediary step where we're doing that phase estimate. So if we make the variational Bayesian assumption that we're only keeping track of a mean and a variance of that distribution, then our best estimate at any given time for the phase of this underlying this stimulus is a normal distribution with some mean mu that entrains to the hidden phase and a measure of uncertainty or variance C. So then the question is, what type of data are we using to inform phase inference? Inference of hidden state is often modeled using predictive coding type models in the brain, in which the sensory stream is modeled as a continuously fluctuating values over time. And hidden state inference happens through minimizing the errors between predictions of those sensory values and the actual values. But in entrainment, we're usually being informed by the timing of events, especially auditory timing of events. Error is the error we're minimizing is timing error. And predictive coding models as they currently exist aren't actually well equipped to do this over continuous time. And so the formalization that I've come up with here is to assume that events in the sensory stream are generated according to a point process. And that point process has a rate function that is a sum of Gaussian shape functions with different parameters. And so you can have more or less precise expectations over phase. And this function I'm referring to as a temporal expectation template because it refers to the times that we expect events to happen as a function of phase. And we've got these, each one has a mean and a variance and a scale lambda. And then there's also this additional constant term, which says that events can happen that are not associated with a specific expectation at a certain rate. And that's the height of this function at baseline here. And by using variational Bayes methods, in particular point process Kalman-Bucy filtering in continuous time, it's a math that exists, but you kind of have to dig for it, we can invert this generative model and use the events to continuously estimate phase and a mean variance on the posterior distribution on phase. So what does this look like in practice? Well, here we've got a graph that has on the x-axis the phase at which an event occurs, and on the y-axis the updated phase estimate after that event occurs. And so these little plateaus here show that if an event occurs close to an expected event time, then the phase is corrected to be even closer to the mean of that time. But in between, you can see that if an event occurs in between expectations, then this diagonal line says that nothing happens to the phase. And that's actually because that event would be attributed to that background rate of events occurring that are not attached to a particular expectation. And so this phase adjustment gives us the ability to entrain our phase estimate to the underlying cycle. Here you can see the dynamics of uncertainty, where if an event occurs right at the expected time point, then the uncertainty or variance decreases. But if it occurs close to that, it actually increases, signifying an increase in the uncertainty about your entrained phase. And then if it occurs in between, nothing happens. And here we can see actual entrainment to a real heard rhythm. So I'm putting in a temporal expectation template that happens to be a swingy set of eighth notes. And those emphasized or accented eighth notes are expected with a small variance and a strong expectation. And then the offbeats have a larger variance and or weaker expectations. And as you hear a rhythm, in this case, da-da-dum, ba-dum, ba-dum, each of those events is incorporated into a phase estimate. And you can see through the gray shading here that the uncertainty about the phase estimate decreases at each event. And the line shows that phase is tracked through the whole rhythm. And if they're on the right, we can see if there's a phase shift. In other words, all of the timing of a whole set of events is moved up a little bit. That phase shift is quickly accounted for by this model. And there's an increase in uncertainty, but then it catches back up and figures out where it is. And I'm calling this a pipet, by the way. I forgot to mention. It's a phase inference through point process event timing. So moving on from there, one fun effective pipet is that it fails in a similar way to the way that humans fail. So in this case, I'm giving it a very difficult rhythm. Da-dum, bump, bump, ba-bum. And when I do that, a lot of these events coincide with weak expectations. And during that long silence, uncertainty increases and events get misattributed to strong expectation points until at the end, it's just completely bollocksed up. This is very similar to the way that humans fail to track excessively syncopated rhythms. Another really interesting effect of this particular framing of the problem is that it actually predicts that in between events, expectations can warp the progression of estimated phase. And so here you can see that if expectations are very strong, then and expected events are omitted, then that distorts the passage of phase. And when an event actually occurs at the end, it seems like it has happened earlier than expected. And there's actually evidence of this illusion in human perceptual report and tapping data that's been reported multiple times since 1886. And finally, we can actually do inference on both phase and tempo in this way. So if we just give it a forward model that has phase advancing at a variable rate, theta, and theta has some noisy drift, then we can do patipit, phase and tempo inference from point process event timing. And patipit actually accounts for some other interesting human data, showing that if you're tapping along with a metronome and the inter-onset interval is very large, then timing perturbations will be overcorrected for those very slow tempos. And patipit will do that because for long inter-onset intervals, there's more accumulation of uncertainty, leading to larger corrections. And when tempo is corrected in addition to phase, then you end up overshooting the mark. So big question for a neuroscience conference is this neurally plausible? So I've been working with Ani on a working hypothesis for how the beat is tracked in the brain. And our idea is that the supplementary motor area, the neural firing state and supplementary motor area keeps track of the phase of this external stimulus, that the basal ganglia is involved in laying out immediate expectations in the immediate future and sort of setting up that template for you right into the future. That expectations are then projected down to auditory cortex from motor areas via the dorsal auditory pathway. And that event timing errors based on those expectations are then relayed up the dorsal auditory stream. That process may involve cerebellum. We're still talking about it, not sure based on experimental data. And finally, an important part of this whole system is that certainty or variance of these phase estimates is tracked over time. And there's reason to believe that striatal dopamine plays the role of an index of temporal certainty. So we've got a preprint on that, which I'm linking to here, and I can put into the chat after I'm finished. I want to thank Tom Kaplan and Ani Patel, Nori Jacobi, Ed Large for very helpful conversations, and Carl Friston for one very helpful email. I think that's all I've got to share. I'd love to hear your thoughts and questions.
Thank you, Jonathan. That was really exciting and interesting, and you're ahead of time, which is fantastic.
Great, great. The nervousness plus practice turns into rushing.
Right, yes. So we have a few questions coming in. So I'm going to, they're not in the question answer, so I'm going to read it to you off of the chat system right now.
Yep.
So one question is, how does your model calculate frequency? Does this calculation suggest or reject possible neural substrates?
Yeah, so the question of, I mean, I guess by frequency, we're talking about the period of the beat or the tempo. Yeah. And for that, it starts with a prior, it starts with some distribution over tempo. And then based on that, it's doing this variational inference on both phase and tempo. And so when an event occurs early, then both the phase and the tempo are updated to a posterior distribution based on the fact that thing has happened. And so it's all done through this variational Bayesian machinery. That leaves out the results that suggest that tempo updating may need to be conscious. And so it's sort of a first approximation here. In terms of neural substrates, the way we're thinking about it is that that's got some persistent representation in prefrontal cortex, dorsolateral, possibly prefrontal cortex. But yeah, our thinking about the neural substrates of tempo inference is not as developed as phase inference.
Right, great, thank you. The next question is the point process a convenient assumption for formal purposes, or is it really worth throwing out a lot of continuous process?
So, so formally, I mean, it's very useful. I feel like it's the best mathematical tool we've got to talk about timing. This model can quickly be extended to include continuous input as well. That math also exists, and I'm just leaving it out for simplicity. And so you can take both continuous and timed data and integrate it into an inference about phase. So you don't need to throw out continuous data entirely. I mean, I think that the assumption that events are generated as a point process, I mean, we also end up with the possible generality of introducing history dependence, which again, I leave out for simplicity, but this would lend itself to that. And once you've got a point process with history dependence, that's really as much generality as you could possibly need to describe event timing data as it comes in. So I think that it's a mathematical structure that really doesn't limit you much at all once you are willing to bring in history dependence and optional continuous data.
Thank you. I have questions for you, but I think in interest of time, I'm going to wait a little bit longer. And thank you again for a wonderful talk. and starting us off.
Thank you guys for coming.
And if you could stop sharing your screen, we can get going.